Hi all, welcome to OS2 Lab Tutorial Video 4. Today we will cover the second part of JOS Lab 2, Virtual Memory Management. Before that, let's recap on what we are doing in Lab 2 at the high level. In Part 1, we managed the physical memory, and what it means is that so we try to mark that some of the used memory by the peripheral devices and also the used physical memory by the JOS kernel itself. And then we need to mark all these pages as are in use in physical. And also we need to maintain all the free memory pages. And also we need to have some of the mechanism that we can allocate the memory and free them. And to support that, in bootlock, we managed to allocate the free physical memory to kernel. And in page init, we mark in-use pages to manage free physical pages. So we are actually marking the in-use pages to get the list of the free pages. And then in page log and page free, we can allocate more physical pages if we need more memory. And we can also return back if the page is not in use anymore using page free. And this is about managing the physical memory side. And in part 2, what we will cover today is about managing virtual memory. And unlike part 1, managing physical memory, we will allocate the virtual memory space at the virtual memory side, and we will back them with the physical pages like this. And we can also set up permission bits in page table entry for controlling memory access for these two pages are read-only and these two pages are read-writable. Yeah. And also can have a different permission mapping in page table entry for controlling memory access. For example, for JOS kernel, we can have additional mapping for the we can have a virtual mapping of the JOS kernel address space, and then we can mark it as like the kernel read-only and user no access to protect the JOS kernel from the applications that will run later in our JOS. And we will finish this the feature of backing the physical page for virtual memory allocation and these kind of the permission setup by implementing the following 5 functions. And before starting the part for today, let me note some of the important points and tips in doing lab 2. First of all, please do not get confused when you need to use a virtual address and when you need to use a physical address. And to indicate the virtual and physical address, in this slide, I will use the red color to indicate virtual address. Basically, all addresses that, and then I will use a blue color for indicating physical addresses in this slide. And basically, all addresses that you will apply memory access in your C code, these are all virtual address. So for example, you are using the variable next free. So that variable contains a virtual address. So if you access the memory in C, for example, if you apply array access or zero out the content using memset, you have to use virtual address because we enabled paging in lab 1. So our CPU can access memory only with virtual addresses. There's no way that we can access physical address. But in some cases, we have to use physical addresses. One example in bootlock is that for bootlock, we need to know that where is our limit of the physical memory. And the maximum size of the physical memory that can be calculated by n pages multiplied by page size. Because we have this much pages and each page is sized as a PG size, which is 4 kilobyte. Yeah. And then we want to compare this limit with the variable next free, but the problem is that the variable next free contains a virtual address, but this size of the physical memory, that will be just a physical address. So to compare the variable virtual address variable with the physical value, yeah, then we need to translate this virtual address to physical address. But within the kernel in lab 2, we can directly translate the kernel virtual address to physical address by using the macro pgdir. So by wrapping the next free variable with the macro pgdir, then we can get the physical address of the next free, and then we can compare this value to the limit to check if our memory usage is out of the limit or not. So this is one of the example. So in this slide, you can safely regard all the blue color text are indicating physical address, and all the red color text are indicating virtual addresses. And in case if you don't know if your current variable stores a virtual address or a physical address, you don't know, then just try to print it. Then, if your address is starting with the 0xf at the start, so for example, if the address is in the range of the f0000000 to ffffffff, then the address is a virtual address. So we basically, so in bootmapregion, we basically map like starting from the current base, and the current base value is actually f0000000, and until the end, we will map this virtual address directly to the physical address starting from the 0 to the ffffff. So these are virtual address. But if you are seeing, when you print out the address, if you're seeing that the address value is not starting with the f at the high bit, so for example, not with f000 something like this, then the address will be the physical address. And next is about page init. So in lab 2 part 1, some of the students are struggling with implementing page init. And to finish the function correctly, please refer to the memory mapping presented in this slide. So this slide just visualizes what has been mentioned in the comments of the code in the page init. So page 0 must be in use, and we will mark starting from IO physmem to ext physmem, we will mark them as in use. And the kernel code should be in use, so starting from external physmem to end, that should be in use. And also we are using the memory starting from the kernel end to the next free, so those areas must be marked as in use. So if you mark this and starting from here to there, mark all the pages in use and link all pages with if ppref is 0. So for the in-use page, you need to mark the ppref as 1. Yeah, then you will be fine. So please compare your implementation with this visual diagram and make sure that you implemented it correctly. And if you do so, then you will pass the assertion check in the lab 2. For the other things, in page.alloc, what you need to do is get a free physical page from page free list and cut the head and move the head to the next. So page.alloc means that I need a page, so please give me a free page. And we have prepared that the page free list as a linked list starting from the head as a page free list. So whenever there's a page.alloc call, then what you need to do is cut the head, move the next as a head, and then return the head. And then if the page.alloc is supplied with the flag alloc 0, so you can check that by if the alloc flags and the operator here is just getting the the flag value of the alloc 0. Yeah. And then if that value is 1, then you need to run memset 0 the page, because you need to wipe out the content of the memory page that will be allocated by the page alloc. But as I just told you, when you run the memset or like the applying some of the memory operation in C language, then you need to supply the virtual address here. But the page alloc and page free list, these will be playing with the physical page, and we will use the struct page info pp to point the free pages. So in that case, you need to change this struct page info to virtual address. So in doing this, running a function called a page to kva. So this will change the struct page info to kernel virtual address. Yeah. So the running of this function and then putting this address into memset will help you. And in page free, so you might think about like managing the ppref value, because when the pages get freed, then like it should have ppref value as 0. But please do not adjust ppref here, and because the value will be automatically controlled by the page.graph, so we will use page.graph to decrement the page ppref, and when it gets to the reference value gets to 0, then it will automatically call page free for that. So in page free, so you can think it as like the ppref is already 0, then just manage the page free list. So you need to add like the newly coming page to the head of the list, and also you need to maintain the linked list of the free pages. Next is about assertion errors. When you run the JOS using make QEMU nox or make grade, you may encounter many assertion errors like this. Assertion failed in some of the lines of the code. Yeah. These assertion errors are raised by the function dedicated to check something. So the function name is a check page or checks allocation or something. And these check functions are there for checking the correctness of your implementation of Lab 2. So if you encounter this kind of the assertion error, this means that your implementation is incorrect. So please take a look at the code line around that point. So for example, open the kernel/pmap.c and take a look at their line 695 and then around that code, and try to understand what this assertion wants to check. For instance, if I go to my current pmap.c line number 695, I'm seeing that this code is checking that like the value must be 0, so it gets the virtual address of the page and then checks the contents of the page, and then all the contents need to be 0, and it checks for functionality of the alloc 0. And after understanding this, you now know that this is raised by page alloc because it's related to the alloc 0. And checking the page alloc will reveal that you forgot to memset the target allocated page if the flag is set with the alloc 0. So if you encounter the assertion error, take a look at the code line near the assertion error and then try to understand what these kind of the code snippet would like to check, and then understand why your code fails. And then take a look at the corresponding implementation and fix it, something like removing the comments in this case. Yeah. Then you can pass this assertion error. And for the correct implementation, you need to pass all the assertion error. So you will see no assertion error at all for the correct implementation. And I have prepared a commented version of each assertions. So please visit the following website that I created just today. And then if you visit that website, then it will show some of the check functions in the kernel.pmap.c, but it will include more detailed comments that help understand about what the code wants to test about your implementation, and then what is the exact case the test case would like to check. And these are for exercise 1, and today we will cover exercise 4, comprised of the following 5 functions: pgdirwork, bootmapregion, page lookup, page remove, and page insert. Yeah. And these are for linking virtual addresses to a physical address like this, and also setting the permissions by using these kind of the 2-level structure, the page directory and page table structure. So you need to be aware of this kind of the 2-level, starting from the CR3, page directory, page table, and we use a page directory index for the top 10 bits and page table index for mid 10 bits to get the physical address. One thing to note here is that this blue color here is an exception. This is a virtual address, and then this red color is now the physical address. The first function that we need to implement is pgdirwork, page directory work. The objective of this function is to return the address of the page table entry. So what we're gonna do is we will be supplied by this pgdir. This will be this page directory. And then we will also be supplied by the virtual address, a virtual address. So there will be a virtual address like this. And then what we need to do is, using the virtual address, we will index this page directory to get the address of the page table. And then we will also index this page table using the page table index in the virtual address here. Yeah. And then get the page table entry. And then we will return this address of this page table entry as a return value of this function. And to do that, we need to get the page directory index and from the virtual address, and we can easily do that by wrapping the virtual address using the macro pdx. And then by using this index, we can index page directory to get the page directory entry. So the result of the addressing indexing the pgdir with this index, it will get this page directory entry. And then internally, after getting the page directory entry, we need to check if that entry is valid or not. And for the validity check, what you can do is you can apply the AND operation to the value of the PDE to get the PTEP. And then if this value is non-zero, then that means a flag is up with the PTEP, so the page directory entry is valid. And if the page directory entry is valid, then we need to get the page table. But the problem here is that this PPN is a physical address. So if you apply PTE-ADDR to the fetched PDE, then it will get the PPN as a physical address. But because we cannot access physical address directly, we need to change this physical address. That's why it is marked in blue. We need to convert this physical address into kernel virtual address using the macro kaddr. Then we can store this address as a PTET, it should be PTE, yeah, PTET pointer page table. Then now we have this table. And then, because the function requires that we need to return the address of the page table entry, so after having this page table address, we need to index page table with PTX. So here we use PDX to get the top 10 bits, And here, because we are accessing the second level page table, we need to use ptx to get the second 10 bits from the virtual address as an index. Then we will index that amount and then return the address. So, and here we'll take the address of this page table entry. So it will basically return the address of this page table entry. And this covers the case of a valid page directory entry. So when the PD and the PTP is valid, then we do this. On the other hand, if the page directory entry is invalid, then we need to create a page table. So if the flag is not set with the PTP here, means that there is no corresponding page table allocated by this entry. So we need to allocate the memory page to create a new page table. And to do that, we need to first check this create flag. If that is 0, then we just need to return null, because this create flag means that don't create any new page table. Yeah. So in that case, we will just return null. But if the create flag is 1, then we need to create a new page table and return that. And to create a new page table, how can you do that is you can allocate the new physical page by using the function pgealloc. And because we will put this page as a page table, so we will use it. So let's mark that we are actually using that by increasing the ppref by 1. So newly allocated 1, the ppref of this page will be 0. And then we will increment by 1 because we have a 1 usage as a page table of this memory block. So we mark that. And then, because we've seen that there's no value of the physical page, and then the flag was not set with the PTP, and then we will put the physical address and then set the flag with the new allocation. So what we will do is get the page directory entry, and then we will store that. So we will take, so because this is the page object, so we will run the page to PA to get the physical address of this page, and then we will concatenate flags P, U, W, yeah, to let a page table have a full privilege for the page flag control. And after assigning the new page table, because this function requires us to return the address of the page table entry pointed by the virtual address, now we can access this page table and get the index and the address of the entry. And this concludes the implementation of the page directory walk. So basically, it will walk down these 2-level page directory and table structure, and if the page table is not existing, we will need to allocate the new one, and at the end, we will return the address of the page table entry. And let me note about the color here again. Please do not get confused between the virtual address and the physical address. And in C code, all the variables that we are using is virtual address, and if you print it, then you will see that it will be starting from F at the top digit. And all the addresses stored into PDE and PTE, yeah. So this kind of the PPN part, yeah, these should be physical address. So if you print the address, then it should not have the top digit as an F. And the next function is about the bootmapregion. The objective of this function is mapping multiple virtual pages to physical pages contiguously, starting from the virtual address VA for its size specified by the size variable, to the address space starting from physical address PA up to size. So the different thing is like the using of the page log and then the mapping a page would be sum up the mapping like this. So the important point here is that this memory allocation is virtually contiguous, but it doesn't need to be physically contiguous. But what we are doing in bootmapregion is that we want to make the virtually contiguous space need to be physically contiguous. And this is required for like the setting up some of the operating system related feature and the hardware. So we just use a bootmapregion for the lab 2 and then early stage of the lab 3. So you can regard that this is a special function. So please just do the please just implement the function as the description on the code, and please do not increment ppref because the mapping created by the bootmapregion will not be counted as an actual use. And next is page lookup. The function is about getting the mapping information about the virtual address at VA. Yeah. And the objective of this function is two-folded. So it has two return values. One is the function need to get the address of the struct page info, so it will return struct page info of the physical page that corresponds to the virtual address. And the other is that it will return the page table entry to the via the variable PTE store. So this variable is asserted as a double pointer, so you can store the PTT pointer to this variable, so it will have two return values. And to implement this function, to get the page table entry, you need to run the pgdirwork using the pgdir and VA. But at here, because it's just for lookup, it's not about the creating the new mapping. So you can use pgdirwork with the pgdir and virtual address, but the last create flag as a 0. Then it will not create the new mapping, but return either null or valid page table entry. If the mapping is not existing, then it will return null. Yeah. And then if the PT store is not null, then it will store the returned page table entry address to the PT store. This is how you can return the address of the page table entry using the PT store variable. And you also need to return the struct page info, and you can get the address of the struct page info from the physical address. And after retrieving the page table entry, if you take a look at the page table entry, for example, so page table entry look like this, and then if you take this ppn, then you can get the physical address of the mapped memory. So after getting the physical address, then you can run PA to page to get the corresponding page pointer from this physical address. And next is page remove function. What it does is that it releases a virtual to physical address mapping at the virtual address VA. So page insert is about like the creating mapping, but the page remove is a removing mapping. And to do that, we can get both page table entry and the struct page info object using page lookup function. For example, for a given page directory and virtual address, if you run the page lookup, pgdir virtual address, and then ppt, then if the mapping at the virtual address exists, then it will return valid values for pp and pte. Otherwise, it will return null. Yeah. So when it is null, do nothing. But if there's a mapping, then you need to unmap the page table entry. So to do that, you need to just set the page table entry as a 0. then it will zero out all the flags, all the address, so it will make your virtual address no longer mapped to the physical address pointed by this page info pp. And because we just released the one use of the physical memory appointed by pp, so we will run page.graph pp. But if its ppref gets 0 internally in page.graph, then it will automatically call page free. So when the page gets free, then it will automatically get onto the page free list. Last but most importantly, you need to run the TLB invalidate with the pgdir and va whenever you update the page table entry. And this is because like a TLB is a cache in the CPU, and what CPU has cached could be different with what we just updated, because that information is not automatically being tracked. So whenever we update one of the page table entry, then we need to invalidate that entry in TLB. So you need to run TLB invalidate. Please don't forget to run the TLB invalidate in page remove function. And the last function to implement is page insert. This function is for mapping a virtual address VA to physical address pointed by struct page info pp with the permission specified in perm. To this end, we first need to get the physical address of the pp, and we can easily get that by running page to pa. We can get the physical address of the pp, because we need to bind the physical address of this one with the virtual address of the virtual address VA. And then we need to write that information in the page table. And to get the page table entry, we already implemented the function pgdirwork. So put pgdir here, virtual address here, and page insert is creating a new mapping. So we use the number 1 for the create argument. Then it will return the address of the page table entry. And then we will finally assign this physical address to the page table entry. So pp is a virtual address, and then get the physical address of the pp by running page to pa, and then change that to the only remaining the top 20 bits. So you can use macro pte addr to get the page table address of the pointer. So wrap macro and function like this, then you can get the physical address of the pp, and you can also attach permission flags. And then because we just created a new valid mapping, so we add a ptep. So this is basically, you need to get the physical address of the pp, and then page table entry from virtual address, and connect these two with the permission flag. And in page insert, there is one special case, because if the PTE corresponds to a virtual address, has already existing mapping to a physical address, then we need to unmap it. So for example, we will run pgdirwork like this, but if you check a PTP of this flag, if that is non-zero, that means that this virtual address has already been mapped to the physical address. In that case, we need to release that physical mapping and put this new physical page to the virtual address. And this sounds like easy, but there is one corner case. So the case is that, think about the case that if the PP and VA combination, so VA is mapped to a physical address, and if that address is the same as the physical address pointed by PP, then there is a problem. So please read about this kind of the corner case hint thoroughly, and then think about the case, and please wisely avoid that case and handle the error conditions correctly. And if you don't do it correctly, then you will encounter lots of insertion error at the check functions. So yeah, so this part is quite important. And next is about some tips for lab 2. First, whenever you update page table entry, please invalidate TLB of that virtual address. So whenever you update the page table entry, then please call TLB invalidate with the pgdir and virtual address. And second, please do not get confused when to use virtual address and when to use physical address. Yeah. And if you don't know it, then print it. So if the address starts with F something, then that's a virtual address. And then for the virtual address, you can store, read, do some of the memory operation. So you can access it as an array or something. Yeah, that could be possible for the virtual address. But if your address does not start with the F at the top, then that means it's a physical address, and you cannot write or read the memory unless you convert it to the virtual address. But for the physical structures, for example, page table or page directory, they do need you to put the physical address of the corresponding page table or corresponding physical page. So please be aware of when to use physical address and when to use virtual address. And for ppref, add one whenever you add a usage to the page. Otherwise, it will be automatically put on the free list, and then you will encounter some of the problems that the one memory page shared by like the many different usage. And for debugging, if you are seeing triple fault, then please run make QEMU noxgdb and attach with gdb, then continue. Then GDB will stop at exactly at the faulting instruction. Then you can use the command bt or like you can examine the values to debug your code. And if you encounter an assertion error, so all the assertion errors are for checking the sanity of your implementation. So if you encounter one, then that means that your implementation is incorrect. So please take a look at the functions starting with the check something and locate the assertion, the line number of where assertion error has been raised, and please take a look at the code around there. And please visit the website that I put the link below. So this code will have a much more description on the comments about like what each of the assertion wants to check, and that will help you understand like what has been incorrect in your code. And then finally, if you want to avoid using GDB as much, which I do not recommend, but if you wish to do so, then please use lots of cprintf to print out all the values, intermediate values, to check your code and implementation is going well. And this is the end of the tutorial 4, and have a nice day.